Now, as you are familiar that we have different types of atomic radii, so we are going to discuss that how these atomic radii vary along group and period. So, first we are going to start with that how they vary along period. Period is that you know that when we move from left to right, periods are actually horizontal rows. So, I have taken here an example of second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So what actually happened, like if we talk about the variation of atomic radii along the period, we'll see that as we move, the atomic radii always decrease. The atomic radii always decrease, because as we are moving along the period, what we'll see that as we move, like I'll take an example of the second period. So if I write the configuration, it will be 1s2, 2s1, because atomic number for lithium is 3. For beryllium, it will be 1s2, 2s2. For boron, we know that it is atomic number is 5. So it is 1s2, 2s2, 2p1, right? And for carbon, it is 1s2, 2s2, 2p2. So what is happening actually, like as we are moving along the period, then the shell remain the same. See, every element in the second period is having a valence shell as 2, right? So as we are moving along the period, that means the electron is added to a same shell. I'll write here, as we move, the electron, the new electron is added to the same shell, right? That means a new electron is added to the same shell. And when the new electron is added to the same shell, two factors are operating. One is the increase in the nuclear charge, because if we talk about this and this, obviously only one electron is getting increased. If we compare this and this, only one electron is getting increased. So we can say that as we are moving, that then the nuclear charge increase by 1 unit, because only one electron is being added. So obviously the nuclear charge increased by only 1 unit. Like beryllium will have 1 unit more nuclear charge than lithium. Boron will have 1 unit nuclear charge more than beryllium, like so on. So definitely, like as we move, we have seen that a new electron is being added, and due to which two factors are operating. One is that nuclear charge is increasing by how much amount? By 1 unit, because there is an addition of only 1 electron as we move from one step to another. And another thing what we see is that, like as the nuclear charge is increasing, and moreover there is an increase in the inter-electronic repulsions also, because electrons are number of electrons are increasing in the same shell. So obviously there will be increase in inter-electronic repulsions also, right? So these two factors are operating. But what we see that as we move along the period, the effect of increased nuclear charge just overweighs the inter-electronic repulsions. That is the reason that the size actually decrease, or you can say the radii actually decrease when we are moving in the period. So I think it's clear from this fact that, as I told you, that electron is getting increased by 1 as we move from one step to another, and obviously there is an increase in inter-electronic repulsions also. But as I have told you that the increase in nuclear charge predominates, that means it is more, its effect is more pronounced as compared to repulsions. That is why the the size is actually getting decreased, the radii is getting decreased as we move along the period. So if we take this into account, that means lithium will be largest. That means the left element, the element which is present on the left side, will be having the largest radii, and the one which will be having to the extreme right, that is, we know that halogens, that they will be smallest. We are just excluding this noble gas. I'll just discuss it later on, right? So if we talk about the atomic radii, that means the one which is present at the extreme left, that is the alkali metal, will be largest, and the one which is present on the extreme right, that means the halogen family, the element of those family will be smallest. But there is an exception that exists. Like if we talk about the second period, then what happened? Like if we compare lithium and beryllium, obviously one electron is being added to beryllium, therefore nuclear charge is more pronounced than the inter-electronic repulsion, therefore beryllium is smaller than lithium. If we compare beryllium and boron, again one electron is being added, nuclear charge is more than the inter-electronic repulsion, therefore size is smaller than beryllium. Again one electron is added to carbon, nuclear charge is more than this thing electron repulsions, therefore size is again smaller. And if we compare carbon with nitrogen, the same thing is happening and nitrogen is smaller than carbon. But a kind of exception you will see here, like if I write the electronic configuration for nitrogen, we know that its atomic number is 7. So if we will write the electronic configuration, it will be 1s2, 2s2, 2p3. That means in the 2p shell it's having only 3 electrons. So they are as far as they can be, and moreover we know that half-filled orbitals are more stable. We know that half-filled orbitals are more stable. So that means here the inter-electronic repulsions will be very, very low. Though they are also possessing the inter-electronic repulsion, but the effect of nuclear charge is more pronounced. In case of nitrogen, what we see that inter-electronic repulsion is as minimum as it is possible. So therefore, the size of nitrogen is smallest of all. The size of nitrogen is smallest of all. Now, if we move from nitrogen to oxygen, we'll see that atomic number for oxygen is 8. So that means the electronic configuration becomes this. So that means here the 2p shell will have 1, 1, 2, 3 and 4 electrons. So as compared to nitrogen, it will have a certain kind of inter-electronic repulsions. That means its inter-electronic repulsion will be more than this, right? So due to increased inter-electronic repulsion as compared to nuclear charge, though the electron is getting increased in the oxygen, like if we compare nitrogen and oxygen, oxygen has 1 unit more in nuclear charge, but still if we compare inter-electronic repulsions, then the inter-electronic repulsions are quite high as compared to nitrogen, because nitrogen is half filled. So that means here inter-electronic repulsions predominate, and therefore the size of oxygen, which should be smaller than nitrogen but is actually bigger than nitrogen, I think you got it. The reason being because inter-electronic repulsions are more, though the nuclear charge is getting increased, but the effect of inter-electronic repulsion is more predominant here, and that is the reason that it is smaller than, it is bigger than the nitrogen. And again, if we move from oxygen to fluorine, whose atomic number is 9 and electronic configuration is 1s2 2p5, so that means it has 5 electrons. It has 5 electrons. So that you must be thinking that here the inter-electronic repulsions will be much more than the oxygen. So it should be bigger than the oxygen, but it's not like that. Though the inter-electronic repulsions are you can say is having a quite high value, because due to filling of one more electron in the same shell, but you know that here the effect of nuclear charge is more predominant. That is the reason that it is smaller. So that means fluorine is smaller than oxygen as per the trend which were actually going. So that means if we talk about this family, then which is the smallest one? It should be in halogen, but it is not actually halogen, it is nitrogen. Why? Because here the inter-electronic repulsions are minimum, and these inter-electronic repulsion effect actually predominate over, you can say it is more, inter-electronic repulsions are very less and nuclear charge predominate, therefore the size is smallest. But oxygen is bigger than nitrogen, but again the fluorine is smaller than the oxygen, because there as the number of electron is increasing, the repulsion effect is increasing, but still the nuclear charge predominate there. So I think you got it. This exception you will come to see only in the second period, and maybe in some other periods where the half-filled and fully filled orbitals are encountered in a period. So now if we talk about the halogen, we know that in halogen the radii which operate is in van der Waals radii, because they have a weak force, right? And we have already studied that the bigger radii is a van der Waals radii. After that we have a metallic radii, and then we have a covalent radii. So that means which is bigger? obviously the van der Waals radii is quite bigger. So as they have van der Waals radii, so that means they will be bigger, not bigger than all, it will be bigger than the halogen. It will be bigger than the halogen. So this is how it varies along the period. I think you got it, that you just need to see that there is you can say a competition between a nuclear charge and inter-electronic repulsions. Nuclear charge is just trying to make an atom compact, that means making an atom smaller in size, and inter-electronic repulsions are just you can say making electrons move far apart, that means they are just making the size bigger. So there is you can say a balance between these two which is operating, and like the one which predominate shows its effect, right? So this is what about that how the the atomic radii will vary along the period. Now if we talk about the group, then I have an example for you, like this is our first group and this is our 17th group of periodic table. So first group is lithium, sodium, potassium, rubidium and cesium, and 17th group you know that is in halogen family, fluorine, chlorine, bromine, iodine and acetylene. As you have seen that like I have written a value for the atomic radii, so you can see that lithium is a smallest in the family, because as we are moving down the size is getting increased. The same thing is happening in the halogen family, fluorine is smallest and as we are moving down the size is increasing. So what happened along group, whether you move in an alkali metal family or you move in a halogen element family, the atomic radii always increase. Atomic radii always increase. Now what is the reason? Let's write an electronic configuration for this too. Lithium is 1s2, 2s1 and sodium is 1s2, 2s2, 2p6, 3s1. So if you talk about the valence shell, then the lithium valence shell is 2 and for sodium it is 3. So obviously valence shell is more for the sodium. The sodium is having 3 valence shell and the lithium is having only 2 valence, means the valence shell is the second one. So obviously as we move down the valence shell is increasing, that means every time a new shell is being added, and we know that when a new shell is being, so I'll just write here that what you observe that new shell is added. So one of the reason is that the new shell is added. But you can see that when we are moving down, the number of electrons are also increasing, and we know that whenever the number of electrons are increasing, then the nuclear charge is also getting increased. The nuclear charge is also getting increased. But and moreover, when we move down, we'll see that the filling of, like I'll write for potassium also, it is 1s2, 2s2, 2p6, as it is 19, it becomes 12. Now it is 18 and this is 19, right. So here the shell is the fourth one, means it is having the valence shell is fourth, and so though you can see that every time as we are moving down the shell is increasing, because its valence shell is 2, its valence shell is 3 and its valence shell is the fourth one. So and the number of electrons are also increasing, that means the nuclear charge is also increasing. Moreover, you will see that as we are moving down, then the number of electrons in the inner shells is also increasing. And we know that whenever the electrons increase in the inner shell, that means the filling of inner shells occur, more number of electrons add to an inner orbitals, then what happen? The shielding effect also increase. The shielding effect also increase. Now what is a shielding effect? Shielding effect is actually, suppose in a room we have a sun here, let's consider an example. Suppose we have a huge sun here and there is a person who is standing at the corner, then what will happen? He will feel the heat of the sun, heat and light of the sun. Now in the second way what we are doing is we are just filling this room with many people and that person is still standing at the back. So do you think that he will feel the same heat and light? No, he won't feel the same heat and light. So that means he is being shielded from the sun by the many people who are in between that person and the sun. So that means he is not getting the same heat and light which he was getting earlier when there were no people in between. So the same thing is applied in this case when the inner shell, like suppose this is nucleus and these are inner orbitals, like, and this is a, let's say, a valence electron. So when so many orbitals are there, the inner orbitals, and obviously there will be any electrons also in it, so that means what they will do is they will just shield this electron. That means they will not allow the original nuclear charge to reach that electron. Like that person when he was standing in a huge crowd, when he was standing there and there were many people between the sun and the person was there. So that person was not getting the you can say same amount of heat and light. So they were actually shielding them. So the same way, let's say these are the people who are standing and this is the sun and this is that person who is standing at the back. So they will not allow the actual charge to move to this electron. So that means this electron will feel the nuclear charge, but the nuclear charge actually felt by it is much less than the actual nuclear charge which is exerted by the nucleus. So this is what is a shielding effect. We'll be discussing later in the chapters, but I think for this moment it's clear. So as we move down, new shell is added, nuclear charge increase due to increase in electrons, and moreover due to filling of inner orbitals, shielding effect is also getting increased. But what we have seen that as we move down, the effect of new shell and the shielding effect is more pronounced. That means this effect is more pronounced as compared to the increase in the nuclear charge. So this effect overweighs. And what is its effect on the size of an atom? Obviously, they are increasing the size. So that is the reason that as you move down the group, every time a new shell is being added, due to addition of electron, nuclear charge is increasing, and due to filling of inner orbitals, the shielding effect is also increasing. But the effect of shielding and the new shell, which is just trying to make the size bigger, is much more pronounced than the effect that is the nuclear charge, which is just trying to make the atom compact. So that means as these effect overweighs, so obviously the size will increase. So that is the reason that whether you move in a halogen family or in an alkali metal or in any other family, the size always increase along the group, right? So this is all about that how the size atomic radii vary along the group and the period.